All right. So first of all, thank you for being here. Thank you for sticking around. It's 8 o'clock or 6 o'clock, and I'm already thinking about dinner and drinking coffee to stay alive. We had some really interesting presentations in the first session, largely dealing with issues of data and data collection and integration into models. And I think that conversation is going to continue in this second session, but it's also going to start to zoom out, as I said, towards the applications of AI and machine learning, for instance, within the notion or conceptualization of a digital twin for the Arctic and what that entails and who it could be for. So instead of me talking some more, I think, again, we can get to the presentations, and then we have a great panel session to round out the conversation. So we'll be joined by 4 guests that I'll introduce later, and they're going to be able to reflect on the presentations that they've heard today and are about to hear coming up, and also try to answer and think about this topic in some of these broader perspectives that have been introduced. So without any further ado, I'd like to welcome the first speaker, Laurent Boutrino, who together with colleagues has produced a presentation or an article or a combination of the two on synergies between data assimilation and machine learning for faster and more accurate sea ice assimilation. Welcome, Laurent.
Thank you. So, I'm Laurent Bertino from the Dansa Center in Bergen. I've been working for the past 20 years in doing data simulation of sea ice and ocean information into ocean sea ice models and doing prediction systems for the Copernicus services. And but more recently, so it's been a lot of focus on how we can really exploit the possibilities of machine learning in our field, whereas 20 years ago we were looking at that remotely as something vaguely, exotic. This is what is our starting point. Our operational forecast for sea ice, they look like this box. We have observations, satellite and in-situ observations, and this is coming from Copernicus Marine Services in our case. We have atmospheric data, so the SMWF, this is also an external input to our models. And the data are assimilated, and they go into sea ice, ocean, and ecosystem models, and then we provide forecast and reanalysis that all go into this Copernicus Marine data store. So apart from the, eventually machine learning that goes into image classification in the input, there is no learning as of this normal, data assimilation routine. The data is assimilated, it provides the output, there's errors, okay, they have the uncertainties in the input, uncertainties in the output, and the errors keep converging to some solution, but at no point there is a feedback loop that says, oh, this was erroneous. That feedback loop, the only one is human. You can see what your system is producing, and then you can learn and you can tune models or data assimilation as you wish. So then, if I'd like to rephrase the problem of data assimilation and machine learning, you can have this wiring diagram here. Either you have data, yes or no. No, you don't. Yeah, you have to make them up. You cannot live without data. You have a model. You may not have a model, in which case it's very easy because then machine learning is your only, way out of this. And if you do, then there must be uncertainties in the model. There must be uncertainties in data. And then traditionally, you use data assimilation, and that can give you something that is unbiased, or it can be biased, and then you have another opportunity to use machine learning in debiasing. So you can do post-processing of your output of the model. That's done regularly now in weather forecasting. It's post-processed to add the missing resolution, but the post-processing, the machine learning can also feed back into the data assimilation. That's what we are exploring at the Dansa Center. And so the uncertainties, one area of improvement, that the model has 2 coarse resolution. That happens a lot because we are using models, many times for the course of data assimilation. We are running ensembles, 100 times the model, so that reduces the resolution. So can we work with that? So there's a method called super resolution data assimilation, in which you can only afford the model at coarse resolution. You may have you may have a model that you can afford at high resolution, but you can only afford to run it once. So what can be done with this is to learn, say, from the model run at high resolution, learn what the change of scale does to the model, and then you can assimilate at higher resolution. If you have learned an operator here, again, the little robot is machine learning systematically, and then you scale up again in the end, and that sort of fixes if the machine learning is much faster than the model at higher resolution, then you can do a work that, say, is taking benefit of the observation at high resolution. So that's what you obtain in terms of here the errors. You can reduce the error by simple interpolation, but you can reduce more with a neural network instead. And then in terms of computational costs, it doesn't cost much more if you have a neural network in your simulation system. So that's what the paper was about. And now the case of CI's dynamics is a bit different, because here is a case when we actually have a model that provides more information in terms of ice thickness than the observations, because the observations are merged from different satellites. They're interpolated, there's kriging involved. So, well, in this case, you would like to actually add resolution to the observations, because you know that there is higher resolution to be taken from. So in this study, then the machine learning is using the model as a training database. And then you want to render the features like the leads in between the flows. So the leads, you know, the leads have an impact on the dynamics. They are, there's shear along the leads more than across. There's divergence. You can have leads as well marked in the concentration, so you can have higher resolution out of the concentration data than the thickness. And this can be included by a neural network that would, say, elude the human mind how to combine that, but the neural network will find its way through it. And then you can add the missing resolution to the thickness. So that's, if you apply that to the model, so your baseline is the smoothed model, the truth is the true model, and the neural network will give back the movement and the missing scale. So that's what you can do on the model data, and you notice this is an area quite large north of Svalbard and Greenland. Now you port that again to actual data, so real satellite data, and then you lose a bit of the domain because you don't have all of the information close to land. Say the ice drift is cut near land, and so in the middle panel you have the application with sea ice drift from passive microwave and scatterometers, so the coarse resolution data. And to the right is the SAR data, so it's much higher resolution but poorer coverage. Still, that's a demonstration that the neural network can be ported from the model data into real data without adjustment. So that's transfer learning in some sense. But it's only giving one solution. And as we've seen earlier, the next issue is to render the sharpness in the results. And having one best estimate often is inherently smoothing the output. If you minimize a root mean square error, by default, the smooth solution will give you the best scores. And that's what we are now looking at into diffusion models, because we want to have generative machine learning, a machine learning that can take you not only one solution, but generate as many as you wish in a cheap way. So here, that's, say, an example of the same type of, say, sea ice thickness, again. And one of them is the target data. And, well, I can challenge you to find which one it is, because they will actually all look quite realistic. So that was a true image. Thank you. So, okay, I know it's not a fair game. And then if you have generated many possible outcomes of the true image, you can calculate the spread, and you will see that the spread, so the deviation, standard deviation between the outcome increase close or into the leads. And that's where, because there's difference of positions of the leads in different simulations. And then you can have these reliability scores that are, say, you can do all the usual diagnostics you can do out of an ensemble of models. Yeah. So smooth target, I don't need to go back to that. So that was the part of the resolution. And the part on being biased and having to process the outcome, that's something we've thought of for, again, the case of ice thickness, in which, so you can re-inject, say, the neural net into the model and try to assimilate again and converge to a better solution. So that's something that has been done, say, on idealized model, Lorentz equations. And now what we'd like to do is to do that for sea ice thicknesses, because we have a model that's biased, okay. We have observations of ice thickness that, again, is the CS2SMOS data, Cryosat and SMOS merged together, but only for a short period. It started in 2010 with the two satellites, well, coincidentally, been run at the same time. So we'd like to now learn from two model runs, assimilating or not assimilating the ice thickness, and then try to learn from the differences and rewind the movie backwards and see if we can have an extension, say, in the past of the CS2SMOS dataset. So that's what Leo Edel is doing in his postdoc, and the technique is here long short-term memory. So I won't tell you why we chose that, but it's to do with language processing and memory of processes. So where we are going to is that we have so far, say, an estimation system. We'd like to include, say, bias correction by machine learning. That's something that is already going on with, say, a collaboration with Met Norway, with Cyril Palerme. But then, with the super resolution parameterization, we want to have machine learning between the sea ice model and the assimilation, both ways. And then maybe in the future, well, that's really following what the work you've seen from Met Norway earlier, it could be possible as well to just scrap it all and have an emulator to provide the forecast, while still needing the assimilation system to provide the learning database in reanalysis mode. So that could be, say, a way forward that we can look forward to. Yeah. That was it. Thank you.
Thank you very much, Louis. Any questions? No questions?
Crystal clear? I don't believe that.
Thank you very much.
Thanks.
Next, we will have a return visit from Sarah Aprecio, this time on artificial intelligence in Svalbard, the outcomes of a training course.
Hi again. This time, this presentation is not going to be technical at all. It's going to be about my experience and the outputs of a training course that we did in Svalbard in September of 2022. I joined SciOS as an observer of the remote sensing working group. This course takes place in situ in Svalbard in September, and it was a lot of fun. I helped to co-organize it, and I was also a lecturer myself, and that gave me a lot of insight on the best approaches to train beginners on AI. Just to a bit of context, SciOS, for those who don't know, stands for Svalbard Integrated Arctic Earth Observing System. Sorry, this is another acronym, very long. And SciOS has several infrastructures around the archipelago of Svalbard. And in a nutshell, one of the main activities is data handling, storage, and delivery. Also, Earth observation data. They have a portal where you can request some of this data. Another is to serve as an interface between scientific platforms and users. Another activity of SciOS is as a facilitator for scientific integration. And also, one thing that SciOS is very interested is to make people use the data and also to learn more about Earth observation data and how to use it and how to process it. So it invests a lot of also training. We have webinars online, and we do these training courses annually So there are multiple outreach activities that SciUS is involved in. If you are more curious about it, go to the sciusvalbert.org and you'll find more information about this. So, as I said before, there is annually a training course that SciUS has. And this year that I was the observer, so in charge of doing this, helping to co-organize it, we were thinking, what is the theme of this year? And AI popped up because of its the trendiness of AI. And also one of the main reasons to pick up AI was that with the thought that we should empower people, new early career scientists to learn more about AI, also to help to exploit more the ongoing production of data in the Arctic and also data from SciUS itself. So there was these two main objectives. The four main components of the course, we did this, the graphics, we wanted them to be appealing and we promoted on social media to attract people to apply. It was mostly aimed for SciUS members, but also once we filled the spots, we opened places for other people. And the main components were to have theory lectures, hands-on and exercises. This was very important because just sitting in a room learning about AI all at once might be a bit overwhelming, so we wanted to make sure people learn the theory and then play with the data itself. And then we also, since we are in Svalbard, we needed to have something in situ, so we tried to combine something in situ with AI pipelines, because normally you just sit on a computer, but trying to be in the real world and see how it connects to AI would be exciting, or so we thought. And then we also had mini projects. In the month following the course, students were invited to develop a small AI exercise, and those who did it would have credits for their master and their PhDs. So we also had a keynote speaker and the lightning speakers, so they would introduce their main applications of AI. They will talk about their own research. And then we also had the lectures itself that will be there physically during this 5-day course. So the main goal was to be aimed for AI beginners, although we had some people that already had some experience. We wanted to teach them how to treat the data, prepare the data. We want them to know, to have the overview understanding of AI in the different branches, and also to develop themselves and use collaborative tools to develop AI pipelines. And what was the actual content of the course? We wanted, it's a lot for 4 days, because one of them was entirely dedicated to one visit. But we wanted to provide them with an overview of AI, the main branches, supervised and supervised learning, the main algorithms of machine learning like random forests, support vector machines, and so on, and also go deeper into deep learning, which we left for the last days. So just a chronology of how it went. On the first day, we had the first focus on preparing the data, curating the data, labeling the data, making sure you have good training data, because this is repeating myself from the last talk, having a proper data set is crucial for a good result of your AI algorithm. Then we had the morning, we had this theory, and in the afternoon we had the hands-on. We have multiple types of different exercises, from sea ice classification, from land change detection, which was one of the examples for the second day. We also had the lightning speakers would also give their own examples on the most diverse type of applications, because here we didn't have only remote sensing scientists or early career scientists. We had people from all fields, from biodiversity, from ecology, remote sensing people. So even though our exercises were more aimed to satellite data, we made sure we will include these speakers to talk about other different kind of applications that AI could provide. So the second day was dedicated to make a clear distinction about supervised and supervised learning, making sure these concepts are very inside of the brain. And then we moved to classification exercises and semantic segmentation exercises. And on day 3, it was the day that I was in charge of. We went on the field, and we wanted to create this feeling of acquiring data in situ. So the goal was we went on a valley that the next day we were forbidden to go because there was a polar bear with a cub. So we were very lucky with that. And we were basically doing something as simple as being in a location, taking the GPS location, and this would serve as a training data for the exercise that I made them do in the afternoon. So the goal was to tell them, look, you are here, you know that wherever you are corresponds to a pixel and a satellite image, so you are collecting this pixel and giving a class to it. This was a bit the concept. We also had a drone, so we made this image with Sios, and we actually end up using drone image later to classify the pixels. This is the group. And this is the tool that I used. I went outside from scikit-learn because it's the most standard, and to use Google Earth Engine because it's fun and it's easy to use and gives quick results in visualization. The last day was dedicated to deep learning. We had this amazing lecture. This is online, actually. And the final day, we had a visit to Svalsat. To conclude, these were a highlight of the mini projects that we had. We had someone doing glacier calving front detection using machine learning. He used recurrent convolutional neural network. He was already experienced with AI. We also had someone doing change detection of DIM using unmanned UAVs. I don't want to say the entire word. We also had someone doing wind speed profiles based on in situ data by Sios, created by Sios. We had also the exercise that we did with Google Earth Engine. We did someone making change detection between summer and winter. And we also had someone mapping lakes using SAR on land, which is easier than doing on ice, unfortunately. And we had this, also we presented online the results, the experiences, and they presented to the community about their experience. Finally, we ran a survey to understand what were they feeling about this, and the overall impression is that they like the course, and they grasp the main concepts of AI, even though it's very short to be familiar from all the machine learning and deep learning algorithms, but also the fact that they were in the context of Arctic and making the connection of collecting in situ data and later using it on an exercise. It was a great part of the fun. And that's it. Thanks for your attention.
Thank you very much, Sarah. Any questions for Sarah on this interesting presentation? Any questions online? I don't know if I know quite how to ask this in the right way, but obviously this was, you presented that this was a gathering of mainly master's and PhD students. And it made me wonder to what degree this recent evolution of AI and machine learning, and whether people call it some sort of paradigm shift or not, but to what extent have you experienced perhaps a capacity or competence gap in terms of Earth system science or climate change science in the current workforce in this field, in the ability to actually start working more and more with these tools and opportunities? Are people trained? Are people ready for this transition? Or is it also a point about the need of training people through the education system in relation to the people that are already working as researchers and scientists?
I think one basic need, at least for now, because there are already platforms where you don't need it, is to know a programming language is already a great asset. And this is a gap existing because there are a lot of people interested in doing AI. And right now, doing AI requires for you to know Python or R or JavaScript. So this is actually one basic need and the major gap that I witness. Again, there are already existing platforms where you don't need to know a single line of code and you can perform AI. You just provide the data set you want. You say, well, I think it's called MLOP. I'm not remember the name, but already exists ways of doing AI without knowing a thing. But I would say this is the first. And then the second, but this is obviously, it's natural for someone who never worked with AI. I think a big gap is to not know all the big branches that exist in AI and also not knowing exactly what is your exact question to solve. Because people, when they have a problem, they say, maybe with AI I can do this. And they don't know exactly, do you want to predict a value? Do you want to identify a class? Sometimes even the problem starts on the question you have to solve and then understand if even you need AI, if you need machine learning or deep learning. Because different problems and different sizes of data, of types of data will influence the type of AI you actually need or not.
Thank you very much, Sarah. And I think SciOS is going to be a network and infrastructure that will come up again in the conversation today. Next, I would like to welcome my colleague, Robert Ricker, who will give a presentation on advancing snow science in Svalbard towards a journey towards a digital twin.
Thanks. Yeah, you mentioned SciOS. Actually, we just will hear it again now. So, and yeah, thanks to the previous speaker because then it's already introduced. So yeah, this will be a presentation about snow science from the remote sensing perspective. And in the end, I will also give maybe a perspective, a vision of how we can evolve this into a digital twin at some point. So I'm at the Norwegian Research Center, and I'm giving this talk on behalf of my colleagues. I also contributed here, but there is also lots of work from my colleagues in here. And I want to start with this figure maybe. Because it maybe gives a motivation why we focus on Svalbard here. Because Svalbard is in the center of climate change and of the Arctic amplification. And we see in the last 4 or 5 decades up to 4 to 5 degrees degrees increase in temperature on Svalbard, and therefore it's kind of a unique laboratory for us, I think, to investigate the impact of climate change on ecosystems, on the climate system, because it's all we have research stations there, we have a lot of sensors there, we have research infrastructure there. In the Arctic, this is a very unique place, I think. So we should make use of it, especially considering the ongoing climate change. Regarding snow, and we've seen this, I think, in previous presentations as well. It's very difficult to observe snow. It's even difficult to observe it just when I walk through the snow, for example, in terms of snow thickness. I'm not talking about density and other properties. But if you ever try to measure snow thickness, you just need to walk 1 meter further, and it can be completely different. And especially on Svalbard, with a very variable topography, it's very difficult to measure snow thickness and snow water equivalent. So therefore, what is needed if you want to improve models and if you want to apply AI, you need a lot of data. And you also need to have like some consistency in your data, like a good representation. And there we come back to the different scales, because of course a satellite will observe something completely different than if you're on ground. And then you have the steps in between. So we kind of need to bridge all these different scales. And this is just an example of around Longyearbyen, for example, where we did measurements, and they're all ingested into SciAS, which has been introduced before. So this SciAS maintains like a huge database, and all these data go into there. And then we can make use of these data to train, to improve models. The party. So we need to take care. We need to find a good strategy to set up those measurements, to find ideal locations for those measurements to improve models. So if we start from the very low, from the bottom of the pyramid I just shown, then we are like at in situ measurements. So we can do this in like in tracks, Magna probe. This is a stick. Just you measure the snow thickness along track. We also have MET stations, but these are of course point measurements, but they have a very good like so the MET stations, then you get a very good temporal coverage, while these are only like occasionally. So they're always like compromises, and that's what it also makes very different to harmonize those data sets. And then we have drones. So this is some involvement, some development over the recent years. Because of technology development, we are able to fly drones, and this is from my colleague Rolf Ohle. He develops a snow radar on the drone, and with this we can measure actually snow depth on a long track with the drone. Here you see the echograms, so you can see this very nicely, the two interfaces. The top is the air snow, and then the snow soil, so to say, interface. And this is very valuable because it kind of closes a bit the gap between ground measurements and airborne or even satellite measurements. And then if we go further to remote sensing, so there are also products existing for snow cover, to measure snow cover with satellites. With the MODIS satellite, for example, there's a long time record, and then we see here we can measure those different snow fractions over Svalbard. Of course, it also comes with certain uncertainties, and you're of course limited in resolution. But snow cover is much easier to measure than snow depth or snow mass, snow water equivalent. Yeah, so coming to snow depth, that's what I tried also recently, is to measure actually snow depth, terrestrial snow depth, using ISA-2, which is a new satellite, and it measures basically, it's an altimeter, it measures the surface height with 6 laser beams, and the nice thing is it's very high resolution. It measures every 70 centimeters the height of the surface. And what you basically can do then is you have a reference digital elevation model, and then you just look at the differences. So you basically have a snow off, snow on model. So snow off in summer when you know there is no snow, and then you can subtract your reference model when you know there is no snow from the measurements you get from the satellite. Of course, you have to do a lot of corrections there. And one issue always is with those altimeter measurements is the topography, because even if you have very high resolution measurements, you have to filter a lot, because if you have very steep, very variable topography, you will get very high uncertainties. But you see here, you get some, let's say, decent estimates with higher higher snow depth where you would expect. We also compared it to some met stations, and it's in the same range, but it still comes with a lot of uncertainties, of course. And you still have, of course, also the coverage issue because it's a laser altimeter, so it won't penetrate clouds, for example. Then what also has been done already is to compare those remote sensing products actually with models and see how good are the models actually that we already have. For example, as Norge or the EBFM. And you see that this is a snow coverage again from MODIS. So we use MODIS as a reference here. This is my colleague Hannah, and you see actually that the models quite differ a lot. So it means like we need to find a way to calibrate, to improve the models, and this is where all these measurements can help in the future. And so if we're able to do that, then the kind of the vision is to develop models, forecast models, so we can actually predict like how is the snow depth in Longyearbyen in 2100. So this goes in the direction of what you expect from a digital twin, right? You want to like click on a map and see, okay, at this point at a certain time you get this kind of snow coverage. But of course, it's a long way, yeah, we need a lot of data. We need to improve the models, and at some point, one idea for a digital twin on Svalbard is, for example, to make a digital twin of the hydrological cycle, which of course involves the snow, but then also precipitation. So basically to close the freshwater cycle over Svalbard, and therefore we need all these measurements. So yeah, I'm not going through the summary here. You can just take it home, and I'm open for questions. Thanks. Oh, yeah.
Thank you very much, Robert. Any questions? Great.
Very short one. What is on board of ICESat-2? Is it LiDAR? Or?
Yeah, it's a LiDAR.
Okay.
It's a green laser.
Okay.
And you introduced and presented the use of drones and radar on the drones for very nicely capturing snow depth. When you mention about the satellite data there needs to be a lot of cleaning of that data. Is it the drones and other in situ observations that you're using to make those corrections? I'm just wondering, what is the machine learning and AI opportunities in terms of the process of?
Yeah, totally. Like right now we use these, for example, the drone measurements. We actually coming spring we want to use the drone and fly at the same time as a satellite overflight. So this is very helpful for us to calibrate also the satellite measurements and to kind of close this gap. So yeah.
That's the fact that you can actually coordinate it in that way too.
Well, we will see, but
Yeah.
it's possible. I mean, it has been done. I mean, it's possible, yeah, but it needs some coordination.
Yeah, very interesting, especially when it comes to the laser and the footprint of 70 meters. How does the topography, are you depending on quite flat topography for that to work well, or?
Yeah, so the footprint is 11 meters actually, okay. So it's and 70 centimeters is the sampling rate, but yes, so I have a certain threshold. I don't know exactly now how it is, but the steeper to topography, you can imagine if you have a footprint of 11 meters. And then it also depends very much on the quality of the DM, of the digital elevation model. So because there are also limitations in there, and there are a lot of challenges here. But yes, so the flatter the better.
Thank you very much, Robert. I'm not doing my job very well because I'm maybe losing track of the clock a little bit. So I'll go straight ahead and welcome Johannes Roers, who will give a presentation on digital twin components for the Arctic Ocean. First, we started with a 10-minute presentation, then it was a 15-minute presentation, then it was a 12-minute presentation, and now it's back to 10. So
Just let me know when there's a couple of minutes.
okay.
I'll round up whenever it's necessary. Yeah, hi. Nice to still see so many people here. It's very late, and I'll try to make this very little technical and very general. Here we are. Yeah, so this is a work at the Division for Ocean and Ice, where I work together with a couple of other people. It's really rounding off what we're doing at Met Norway in terms of forecasting. So basically, I will talk a little bit about our value chain, how we normally do things, and how we're going to do things in terms of ocean forecasting or weather forecasting in general. And I will give an example of pieces and bits of a digital twin, if there's such a thing here. And I will also raise a question, an interesting question here, whether this satisfies some kind of idea of an identical twin that I'm present here. So I'll come to that later. Yeah, go back here. So this is how our value chain usually looks like. We have observations. They are the basis of everything in forecasting. And from there, we go through some processing chain, lots of numerical modeling, post-processing, and finally, the data gets to users. And the users, how the users require forecasts also determines how we're going to make our observations in the future. So there's a feedback loop. A little bit more to a specific example here in terms of ocean forecasting. In ocean forecasting, we often ask very specific questions. For example, what is happening to this iceberg here? Where is it going to float? There may be oil spill. Where are we going to put our cleanup resources? Where do we expect the oil to strand? Or in case of more severe conditions, this is Viking Skya Tystadvika who lost engine. Is it going to go on shore or not? Or where do we eventually need to look for people if someone goes overboard? Sea ice is also a good example, sea ice forecast. So basically, we start with our observation network to get the present state of the ocean. From there on, we're going to run dynamical circulation models for the ocean or for the atmosphere. We have wave models. That in itself is an important piece of the digital twin here, but it's not all. What we need to do is to address the user needs in terms of the iceberg or the oil spill. Often we go to a particle tracking model where you can see the particle. The user can ask a specific question. Here, I've seen an iceberg. Where is it going to float within 2 days? Or if you have an oil spill at a certain location with a certain type of oil, where is it going to end up? So the user has a lot of control over the simulation here and starts a system to kind of produce this data. So I think this comes close to the idea of a digital twin as it is defined now. But of course, we have been doing this for more than 10 years, like this, much more than 10 years. Impact modeling is also very interesting in this concept because here the user can ask even more specific questions about a combination of variables from different models. Okay, so this is how the dynamic models look like. We have a suite of ocean models, one for the Arctic that we developed together with Laurent and the rest of the Nansen Center. It's a very important piece. We have a coastal model here that we developed together with the Institute of Marine Research. We also have a high resolution model for the Barents Sea. So what are these models? Many of you know, but for those who don't, they describe the evolution of the state variables. We have the bathymetry in the model. We model the surface currents, or the currents at all depth actually, temperature, you have a landmass, and that will allow you to predict the future state in terms of these state variables. In addition to that, and that's a very important part in this idea of a digital twin, but also in terms of forecasting in general, you somehow need to make sure that your digital instance is related to the real world out there, and that's where the observations come in. As many as possible. Some are more useful than others. Satellite observations play an important role in observing state variables, but also in situ measurements, gliders, or ship CTD sections. And we are also very proud of these radar stations that we have on land here. You see, we have a couple of stations along the coast now that basically they measure the surface current from land. So from that we get the idea of how's the ocean state today, right now. This is how the system, one of these systems could work. Basically you have your ocean state. What you see here in black is the current speed, and then there are these observations popping up everywhere here and there, and the data assimilation will adjust, for example, the temperature increment, the temperature through these increments, but also the other state variables are changed. So basically this procedure assures that the digital twin remains connected to the real world. All of that put together, in addition, you have these specific components that target user needs. For example, fish farming. You can ask this what-if question. What happens if I put a fish farm here or there in terms of the spread of salmon lice, for example? How do these fish farms connect in terms of the transport of pollutants or lice? In terms of wind farming, where do I put my wind farm in order to get a certain amount of wind, and how do the wind farm impact the circulation in this area? You can ask all of these questions, but it requires that you have an additional layer on top of the dynamical model on the observation that kind of are more tailored to the user, the question that the users asked, and they combine many models. Back to this example here, I was talking about this ice drift. For example, we use the ocean model for the ocean current and the wave model for the waves that impact the the iceberg. You can run a particle tracking model and you get a drift trajectory. So is that the answer? Not really, because I was asking earlier, do we have identical twins? That means, is the ocean current that is modeled by our physical component, is it identical to the ocean current out there? I guess you know the answer. The model has uncertainty, sometimes very low predictability, so it's very uncertain, so you have to address that somehow. And I think that's an important part here. So in this case, for this modeling system, the model consists as an ensemble of 24 members. So you get 24 realizations in this case of the currents. Each of those realizations develop in a certain way. That goes also for the other state variables like the sea ice and the temperature. And that allows you to two things. One thing is to, of course, assess the uncertainty in terms of some standard deviation or whatever you like. But you can also then, in terms of, for example, the iceberg drift simulations, you can run your simulations with each of those ensemble, and you get different results from those. So you kind of span out the range of possibilities that's out there in terms of what you're interested. And in this case, for example, you see that this is an iceberg that is hypothetically observed north of Bjørnøya, and there's some chance that it comes very close to the coast, and then probably goes past the southern side. It may get onto the coast. So you can assess the uncertainty and get some kind of probability. And I think this will be, this is very necessary if you're dealing with the uncertainties or very uncertain models here. Okay, and then this is another example of that. If your ensemble works well, then you can actually distinguish cases of low predictability on the right-hand side here. You see that the different representations of this iceberg from the model, they go in very different directions. In this case, you don't have very good predictability, so you maybe better prepare for all types of scenarios. In other cases, like in this one here, you see there's a very high degree of predictability. So in this case, we have a quite a fair idea of where this particle is going to end up. This is, I think, in this case of this hypothetical case, this is not an iceberg. This would be an oil spill. But all of those questions are very similar treated here. And I think what is also important in this idea here is that the user can tweak the system to their needs. So let's say you have a ship. To what depth does it extend into the water column when it drifts? And when it drifts at the ocean surface, how is it impacted by currents, wind, and waves? Because that depends on the ship type. So the user can provide this information themselves and play with the different scenarios. Also for planning, what if we design our platform slightly different, make it bigger? Can it sustain more wind and waves? Does it drift in different directions, and so on? So you can ask all of these questions. I think this is, for us, a important part, instead of just providing the ocean currents and the waves, we like to be part of developing these tools that are more tailoring the user needs. The last part here in this talk is what is a further requirement in order to make this smooth, is all of the data that may be necessary in order to process your questions. The data need to be managed in a way that it is possible to use it by a range of users. So it has to be somehow stored and made available. And there are these principles here, that the FAIR data principle, that help you to make the data easy usable by AI or specific tools. So data has to be findable, it has to be in some kind of catalogs, it has to be accessible, of course, and so on. So I think that's an important part to kind of exploit the data, and these principles will add value to the data that's already out there. Thanks.
Thank you very much. You're not the first person to finish their presentation today with making comments about data accessibility and data quality. Any questions? Yes.
Hi, that was really nice. I have a question. So the underlying models here, they're like mechanistic models for ocean currents and all that. And I mean, they're based on equations that we put up there, and because we think systems work in a certain way. Now there is this whole new paradigm of deep learning and other ways of predicting, which doesn't necessarily build on like what we think about the system. We're testing them against what is actually happening, more driven by data. So can you reflect a little bit on what role do you think that approach has in the near future and maybe in the far future in the type of questions you're working with?
Yeah, very, very good question. Of course, at times these algorithms will replace the typical dynamical forecast that you described. But as of today, those algorithms will still be trained by the same models. So you still need those models somewhere in your value chain, either for training, so that you can, or in there's often these methods are today applied as a calibration, but even if you don't use them to calibration, if you make them to make the forecast, you still need to train those data. As for example, in this case of this drift application, your observations don't cover everything and at all depths. So you somehow still need to connect the dots, and that is the role of the model in that case.
Thank you, Johannes. I hope some of you have some more questions for him, because you'll be returning for the panel session. So if you have any more questions, there will be that opportunity. But first, we have a mini keynote, I guess we can call it, to round off our series of presentations. I'd like to welcome Ontbora Salberg to the stage from the Norwegian Computing Center, who's going to give a talk on foundation models for Arctic Earth observation.
Thanks. Yes, this will be about foundation models. It will be more like a trend talk because this is quite hot in computer vision and is moving into Earth observation big time now. So we have projects on it. We will not present much results because we are just started it, so these recent activities. But first, a little bit, we have been talking a little bit about Earth observation, and we have seen already that the Arctic, or been mentioned already, that the Arctic is changing a lot. It's maybe faster than the rest of the globe. And this has huge impacts, both for land and marine life and the ocean, everything. And challenging to monitor it. Even here from Tromsø, we cannot just look at the window and see what's happening. We need to use some kind of tools to do it. And remote sensing has been already talked about a lot, that is suitable for observing the Arctic environment. So, saying that, there is, of course, a lot of activities on the sea ice. It's been mentioned a lot of times. ESA is also interested in, for instance, the CCI, the climate change initiative they have. They're also interested in snow. So this is from a project that we are involved with, where we do daily snow cover mapping back to the 80s, using every sensor that is available, more or less. But also the marine and the life. So we also have used remote sensing for counting seals in this case here. This is the Institute of Marine Research, who is conducting a regular service in the West Ice outside of Greenland to do this. And also, what we've been mentioning here, AI is becoming more and more popular here. So for me, AI could be like concept of machine being able to carry out tasks that we consider to be smart. So it's not a precise definition. I don't think there exists, actually. And this machine learning is more like, okay, you have this data here, and you feed that to an algorithm or machine, and you are able to learn from it in some sense to make predictions. And so this has been around for some time. And in the beginning, we had this classical machine learning approach. This is like 15 years ago, everyone was doing this. We had training data here with labels, so we know what we're looking at. We feed that into something, a feature extraction, meaning we try to find a meaningful characterization of what we see and learn an algorithm to separate this. So, and we have new data, we do the same feature extraction, and we get classified. Okay, this is a cat. And this is fine, that it works. And there was one challenge, and that is extracting these features are so difficult. And this is what people have been doing, 80s, 90s, 2000s, extracting features. This has been machine learning. How can we do that? So how can we describe features from these images here? How can we say that this is a dog? Extremely difficult. We have no clue where to start, actually. And so then the performance wasn't that good. It didn't work very well, at least for a large scale or something. And yeah, often we were lacking to be implemented in operational systems and all those things. This changed in 2012 when deep learning came into the role here. It transformed image analysis completely, and also the other kind of data analysis on the data. Deep learning is just a deep convolutional neural network. That is what is often referred to it as. Meaning deep, meaning many layers stacked on top of each other. And this is good. And then this one thing is, this is just, a network is just a bunch of parameters, millions of parameters that are learned from the training data, the input data and the labels. It learned end to end. So from the input image to the prediction that we want. And the good thing about that, there is no more this feature extraction. It's gone because you do that in the learning phase. So that was a really good invention. There's, of course, a shortcoming with this method as well, and that it is so data hungry. So in order to utilize this deep learning here, to have this good performance compared to the other algorithms, you need a vast amount of data. And of course, if you are Tesla, no problem. You have a budget on AI more than Norway have. But if you have these small companies, Snow and Ice Incorporation, and you are struggling, you are barely making it above the classical approaches. So there's a performance gap here. And this has been a lot of focus in the deep learning, at least the last 5 years, and it's starting to change. And one thing that is driving this change is this foundation models. Also in Earth observation, it is even worse, because then you want to generalize across time and space, and you need even more data. Yes, foundation models. So this is, I would say, a shift in constructing AI models. It replaces these task-specific models that we have seen a lot from CEIs to other things, SNO or whatever, with one model, a foundation that can be easily adjusted to a lot of different downstream applications. And the good thing about this model is that it's trained using unlabeled data. And the most famous foundation models that we all have heard of is ChatGPT. It is basically trained on removing a word in a sentence and predicting what it was. That is the foundation. And then, of course, it's adjusted with a little bit training data to answer some questions that we will figure out to ask. And why is this a good thing? Well, it removes the need to develop a huge amount of training data. And so you can learn from it without requiring labels. I will come back a little bit about the learning. And often the performance of this downstream task can be better than if you train from scratch with the same amount of data. And it reduces the cost of building this downstream application can do. And it has the potential for powerful multimodal applications. And this is, for me, the coolest thing about this. So, of course, there's not only ChatGPT, there's a lot of models. PaLM, Llama, these are language models. Vision, you have Stable Diffusion, DALL-E, there's Segment Anything model, ImageN, and you have multimodal models like ChatGPT-4, Clip, OpenClip. A lot of models are popping up now. And also in remote sensing, there are coming models there. Multimodal foundation models. So, how does it do it? Well, it is often based on transformers. I will not talk about the architecture. It's quite complicated. It has been mentioned already. And it's trained using something called self-supervised learning. And that means you are creating a task to solve from the data itself. And one thing I've demonstrated, one popular method of doing that is something called masked autoencoders, where you are masking out part of the image, the same way that you are removing words in training ChatGPT. And you try to predict the missing thing from the remaining. Of course, for remote sensing, it could be a challenge to do that, so you may want to mask out a channel or something else instead. And you're hoping that by doing this, you're able to learn the information and data, and essentially you are compressing the model to really figure out what's in it. So this vector here represents what you really was at the core of the model. And since it's not depending on labeled data, it's scalable. You can just throw more data, and data is available. No problem with data. There's so much data where you drown in data, but the labels and telling what there is, that's the challenge. And there are, of course, other methods. I will not mention them. So this is how basically they do it. Then we can talk about multimodal data. And then you're combining, let's say, images, text, speech, structured data, and you train a foundation model from that. And why do you want to do that? If you think about humans, they normally think in multimodal reasoning. So if you say word dog, you're not just thinking about how it's written, but you are also referring to how it looks like, how it smells, how it moves, it behaves, and all these things. So you have a lot of other information about an entity than just the word. So here we have all this data. You feed all that into a foundation model. It's quite big, and then you can adapt it to a lot of different applications that could be on totally different tasks. You can do computer vision, you can do NLP, or you can do some other stuff you want to do. You name it. This is the downstream task that you do this adaptation here. Yes. So how does it? Why is that a good thing? Well, you incorporate this context when you have model data. You can see how does the sound compare to the image. So you have more information about that. And so this is a strength that, in my opinion, will level up your your ability to learn even more about what you're looking at. And of course, these transformer architectures streamlines all these modalities, because this ChatGPT text, the language model, also uses transformers, and it's quite easy to merge the information from all these modalities. So here is one example, quite complicated. This is from the UAT Machine Learning Lab, Division Intelligence. There's a colleague there who's been working with some other groups and to designing. I already used actually 5 different modalities: image, text, table, video, and audio. And it's quite different, huge model they have created. It took some time to train it, but still, it's only, they haven't labeled the data. So, downstream application, this is important, because this is what we will provide to the society. That is an application that provides a service so we can benefit. And how can we do that? Well, we take this foundation model and we can freeze it, so we can keep it fixed more or less. We can adjust if you want. And then we add a head. That means a smaller neural network that we can adapt using a few labels. I mean, a few, that means a tiny bit compared to what we will need to train from scratch the whole model. And we can, but that designing to work on different applications. And hopefully this is so powerful here that we are able to solve a wide range of tasks from it by adding this head. So instead of having a deep learning model for each application, we are now feeding the data into a foundation model and extracting applications from it. That is the idea. And ESA has also started to look into this. So we have just started a project with them now for creating a foundation model for Earth observation. It's called Foundation Model for Climate and Society, where we are looking at the Sentinel data to train a huge foundation model for using that. And that will be applied to different applications. So we have teamed up with, for instance, NVE for floods, Polar View for iceberg detection, the Romanian Institute of Marine for, no, Institute of Meteorological Institute for drought, and Danish Meteorological Institute for sea ice, to make these adaptations of how we can do it and measure the performance. So this will be a model that we will started last week actually to do this work here. So we will do that for the next 18 months or so. They also wanted a text modality, and this is a requirement, which will be create reports from what we observe, and they write a text report. Okay, we have this and this, describing what we see. Yeah, for snow, for instance, we will consider here just Sentinel-1 and 2, but this is selectable. So if we don't have to use all the modalities, we will just pick the one that we need. So we can only use Sentinel-3, for instance, also it should work. And we feed that to the model, and we can extract like snow coefficient, snow wetness, snow grain size, you name it. I will not say snow water equivalent, because I don't think we can estimate it from this quite good anyway. So, yeah, so these are not maps created from this model. This is created from a classical deep learning approach that we have done a few years ago. So sea ice, you have the same thing, Sentinel-1 and Sentinel-3, and they're also using a passive microwave instrument here. We feed that in. You can take a sea ice thickness, sea ice type, sea ice concentration, and also report all that. So this is an example they did also in the same project we did the snow for a few years ago for mapping sea ice using I think that was a unit approach. But it worked fine. An iceberg, maybe we also use Sentinel-1 here. I don't know if any other satellite will be useful here. Maybe Sentinel-2, but then you have the clouds, and then you're not so sure if you can they do acquisition far in the Atlantic Ocean either. So, and we can get detections from it. So that's the whole idea where we're moving with this foundation model for Earth observation or climate and society. And then there's another thing with these deep learning approaches, and that they are data-driven. Also, this foundation model in itself is quite data-driven. And that is good. You are able to learn a lot of cool stuff, but they are learning from examples. And that could cause some challenges sometimes. So here is one thing that we discovered a few years ago. We want to map forest roads. We didn't do it in optical image, we did it in LiDAR images. So just using optical image to illustrate it. And we got quite good results measured in pixel performance, how accurate do we do the pixel predictions and all these things. I'm quite happy. Then we looked at the roads, it looks like this. So we're capturing the roads, but then you suddenly have a gap from a few meters here. Had no clue why. And this is the problem with it is data-driven, because it's probably having some examples in the training data saying that, okay, conditions like this, it's not a road. So it stops doing that. And of course, this result is fine if you are, let's say, the Environmental Institute. We are just measuring how much road there is in this protected area. It's fine, you can do that. But if you are the mapping authorities and you're relying on building a map of the roads, the infrastructure, this is not useful at all. So this has moved into a new project we have started, which is integrates human knowledge, physics, so constraints everything into these models, where we try to do that. And so this knowledge, I mean, like scientific knowledge could be mathematical equations, typically a partial differential equation or anything else, something that can describe the physics, but also knowledge graphs, which can be built. So for instance, nature has a graph structure in itself, how it's organized. So we can use this information to enforce this neural network to work more consistent how we want it to work. So this is the idea here. And we just started that. We are just picking some low-hanging fruits now in this knowledge graphs thing here. So, and by enforcing a hierarchy in the classification. But the idea now is to take this and put that into the foundation model. So we can have these constraints in here. So we know how, if you have a knowledge graph, how we can modify it by some structure. And then we have two different applications, which is snow and wetland here. So this is something the Research Council in Norway have founded. So this is what we are also focusing in now. How can we improve it? It's not easy, it's super difficult. I must say that. So I'm just hoping we are able to advance it in some direction. So where am I? Okay, yeah. Moving to the end, innovation gaps and challenges. There's a lot. One of these, by this foundation model for Earth observation, is there is huge resolution gaps. There is 10 to 20 meters for Sentinel-2 and Sentinel-1, and 500 to 1,000 meters on Sentinel-3, at least the SLTR sensor, which are mostly used for snow mapping because they want the temperature bands. It's not trivial to solve it. There are some approaches called Scale MAA, which is how we can do this learning of the foundation model, but new solutions may be required here. And also, there is this time. And of course, sometimes you also want to analyze using a time series, but the time is not precise. We haven't a Sentinel-3 observation exactly when we have the Sentinel-2. So something may move, for instance, clothes, all these things differs also. So then maybe need to encode that. And there is an approach called SET-AMA that we can utilize. We haven't tried it yet, which is a challenge again. And missing modalities, another approach. So sometimes we don't have a Sentinel-3 or Sentinel-1 observation, for instance. And particularly now when one of them are dead, it is satellites, so it's even fewer. And then also if you go south, it's fewer observations. If you are here, it's no problem. You have it somewhere in times during the day. But in this equator, it's hard, much fewer observations. So we need a way to handle it. So you need to be robust for missing modalities. And there are also different projections, maybe. I know this Danish Meteorological Institute, they analyze the Sentinel-1 data in a slant range domain because they don't want to project it when you're far up north because it has some distortion. So they do the analysis there, and then they project the product into some graphical coordinate system. So this is a challenge, how should we combine them in the foundation model, which Sentinel-3 doesn't do that. And so, yeah. And there's also no natural text modality for this Earth observation. There's no one who has labeled all the Earth observations, describing a caption to it or something. So this is a challenge we need to solve and figure out if you're able to do it. All right, this is where it's moving. Future, maybe. This is something I've seen, large language model for Earth science. I will not be surprised if there are a few years there will be a language model for Arctic, for instance. They have it for the ocean as well. So you can ask questions and then you can have it in ocean language returned. Climate, definitely. There are already a foundation model for that you can use for forecasting and downscaling and all these things. So and I think it's available also. So you could, it's Microsoft who has developed this one. All right, so conclusions. It will transform the way we use AI in Earth observation, and definitely. And this multimodal data and human knowledge may provide contextual information that enhances the analysis. I hope so, and I believe so. But it has transformed language modeling, computer vision, and are moving into Earth observation. And I expect that you will have foundation models that are tailored to Arctic downstream tasks as well. Pretty sure about that. And finally, there's some catch here as well. This training of the foundation model itself, not the downstream task, it's computational demanding. So you need some high-performance computers like the Lumi server in Finland, and something can help you. Otherwise, you will probably be having some angry colleagues you have blocked it. All right, that's it.
Yes, we're just setting up chairs for the panel session, so you can ask a question now to Anbora, and we can have our other panelists join us up on the stage. Yeah, I think we have time for a quick question while we're getting set up.
Sure, very quickly. Fascinating, thanks a lot. I'm not a technical person, but I just wanted to hear a little bit more elaboration. I mean, you said foundational models don't need a lot of labeled data to train on, but it seems to me that human work comes in other parts of the pipeline, essentially. So, for example, you add knowledge.
For the downstream task.
Yes, exactly.
So you need data there.
Yeah.
In the end, you need to tell the computer what it is. So otherwise, it will have no notion of nothing, actually. So yeah, at some level, definitely. Yeah.
Yeah, maybe I could just do a quick one. Super interesting presentation, because I think so much of the issue in remote sensing is there's so much data and we don't always know what to do with it. Simple question though, how do you handle clouds if you have an area that's perpetually cloudy and models just viewing this as clouds always, but you really are interested in the landscape characteristics?
That's a good question. For now, we are thinking detecting them and putting it as a missing modality for those areas, something like that, and we're hopeful that will work. So we will see. So. Yeah, good question.
Thank you very much. Yes, I can ask our panelists to join us on stage. We have Erik Malnes from Norse from Energy and Technology, and we have Lauren Decker joining us as well. Lauren, where do you come from?
Yeah, hi, my name is Lauren Decker. I am the Chief Science Officer at Polarctic. We are a US-based, let me see, I knew I would forget as soon as I came up. Okay, my silly notes. So we're a private company from the United States, and we're an Alaska Native woman-owned company, and we're doing environmental modeling in the Arctic using artificial intelligence. Currently, we're working on a digital twin of the ocean out of the Bering Sea area, so not the Barents, but the Bering. I keep getting confused in all the talks. Wait, I don't recognize that at all. Wait, oh, okay. Yeah, and so one of the things that I haven't heard here yet is the use of agents within digital twins, and that's one of the things that we're looking at is if you have all of these fantastic models that everybody's building, but then you throw in a little crab into it, how does it behave within that environment? And so I really liked the oil spill example and the icebergs example as sort of the start to that, but then give those particles agency in terms of how will they behave within these digital twins. Okay, so that's my spiel. Shall I pass it along?
Well,
oh no.
I think
hot
just
potato.
Hold on to it a little bit. We have had a great session now through 2 periods, and of course the name was towards a digital twin of the Arctic. And what we have heard already is some of the applications, some of the foundations that we could build on. So there's some tremendous opportunities, I think, for future scientists to take these tools and to further develop our understanding and representation and finding out what will happening in the Arctic using data science and artificial intelligence and digital twins. And we get a bit back to, and we also had a nice, with the Jakob showed us what he was thinking, what is a digital twin, so we probably get a bit back to that too. So the concept of digital twin in the Arctic is something that we will be looking at. What can it provide for us? How could it support our societies? And also, what can the advancement of AI and supercomputing do? Does that mean that we now could model the world in a parallel digital world and then play around with it and see how our actions actually affects this world before we have done it to the real world, which we have done a lot of things throughout the centuries. So if we start then, what should our ambitions be? What should be the goal for using these technologies when they come to the Arctic? Anyone has any input or thoughts about that? Johannes?
I'll start, but
Okay.
I'll pass it over. I feel like that's a very, you can have tiers to that, and that there's the tactical, and then the strategic, and then sort of the North Star. And I feel like the North Stars, we really want to empower and inform people on all the possible solutions. And that's what the big goal is. And then at the tactical level, all the presentations that we saw today were just phenomenal. And I feel like in that middle sort of strategic area, it really is incorporating everything into sort of like, let's go from those individual models that we have that everybody's working on, that are just great, and start integrating them in. So that's sort of my 3 tiers there.
Start to nest them. Yeah. Johannes?
Yeah, thanks. So I think an ambition must be that all these tools that we discussed, they become more applicable for the kind of society needs and the specific user needs. So that kind of means that all of these methods need to be integrated with each other. Data need to be integrated and models need to be integrated. For that, the data has to be made fair and available and such, and you have to build kind of on top of that. And that is something that no one can do alone, I think. So it's an exciting task.
Mm.
Yeah, I guess Europe, EU has large ambitions with this Destiny Earth system that they are trying to build, which of course is somewhere in the future they want to have a digital twin for the Earth, where all the different systems interact. And so I guess for the politicians it's very important to have it easily accessible, so they can ask a question like you do with ChatGPT. How will the avalanche be in Norway in 100 years or something like that? So I guess that's kind of things you want to, and how will that affect the humans living there? So it's very ambitious, but we will have to start with the small pieces, I guess.
Yeah, now you are transitioning very, very nicely to my next questions, and maybe we'll start on going further on that. And that is, what is the potential effects and benefits for society?
Yeah, I think, for instance, this fall in Norway, we had a large flood event called Hans that affected a lot of people, and of course there were warnings, but no, in the end people really were surprised how much damage this flood did to the society, and how deeply it impacted us. So I guess the politicians and the planners want to have a tool that where you could really look into the future and see could you do something to avoid many of these events, for instance. That could be a positive outcome.
Yeah, I totally agree. Yeah, I mean, this is informing the society, and that is what we are aiming for with this, I think, with the vision, and also in a way that is comprehensive, that you can look through, at least when in the end, when we really built this digital twin of the Earth, and you can see across different sciences, for instance, and we are combining a lot of data models in order to have a good prediction, so you can have some trust in it, so you take into account the factors and uncertainties and all these things.
Yeah, you mentioned one thing here, trust, and also you emphasize the complexity of many of the models and understanding them, and we are developers and scientists, and we have but how do the end users, how do you think they would perceive, and how could we make sure that they see these as good tools and trust them?
Define the end user.
Well, maybe politicians and policymakers, industrialists.
That is to have a common people to have a notion of uncertainty, I think, is challenging. So in that they need some good tools to inform them. And I don't know, this is maybe out of my game now.
I think, I mean, what we see is many people do trust the weather forecast, and it's about communication that when we use the same tools to make other types of informed recommendations or decision, it's based on the same tools. So these are the tools that you already know. We're just using them now to answer a different question. That could build the trust.
So I do think that weather forecasting is a really great example of high utility for a lot of people, and you have fishermen that are out there trying to figure out can I go fishing, look at the lows and all that things. One of the concerns I would have with a really big, really good digital twin is who owns it, because you don't want one model to rule them all. You want to be able to have some different groups owning different, the ability to have a model to understand it yourself, know what data goes into it. In addition to the FAIR data principles, there's a ethics group of data principles called CARE, and I wrote them down because I always forget the acronym: Collective Benefit, Authority to Control, Responsibility, and Ethics. And I believe having different stakeholders having trust in the model, Sami people here in Alaska, the Alaska Native corporations, and being able to have stakeholders have that tool at their disposal to understand it themselves is also really important. And if both models say the same thing, there's so much more trust in the solution.
Yeah, Johannes mentioned the FAIR principle earlier, and also what you say here, it seems like there's power in data and ownership of data. And what does this mean for the people living in the Arctic, having these tools? How could we ensure that everyone could benefit from the tools, or would the people with the ownership of the data or the power of data also use this to get more power generally in the society?
I think there's a really big question on who's making the final decisions on a lot of these things. If it's the government that's not collaborating with the people that live in a particular area, you're going to have a lot of stressors, and it's going to be, I think we've heard a lot about that in some of the big talks today. So I just think that collaboration and cooperation and coordination are really important components.
But then,
if we come back to this idea of the digital twins, or the internet, I mean, the internet is a distributed system, no one owns it. And in terms of these digital twins, they're talking about the ecosystem of digital twins. So I think there is there could be vast space of data, the data space or the data lake, and there could be an ecosystem of models and tools so that everyone can access them. And of course, the data has to be openly available. That is the only way.
Yeah. And this takes me to one of my last questions. What do you see as the barriers for getting this technology out and getting the benefits? What is stopping us now? Is it still knowledge of the models and developing them, or funding, or ethical challenges? Or
good question.
I guess some of the things are really like what the EU is doing to provide data to free of charge. That is democratizing the access to the data. But of course, models are not like that. So and also there are some, for instance, for crunching all the data you are doing on running on machines, they are owned by someone, and in the end, like even Google wants to earn money on this. So it will be interesting to see how that develops in the future.
Mm. Yeah, you already mentioned the big data owners today. Do you think that they will be opening up access to their data, or?
Data maybe, but not computational facilities. I think that's because that's a power consumption, and someone needs to pay for it, and so that is, yeah, that's a challenge. And even as a scientist, going to LUME, which is a European initiative, costs. So it's not free.
Yeah. Yeah. So my last question then, when it comes to thinking about this, should we be scared or should we be happy?
I'm not a scared person, so.
So you're happy.
Yeah, I think it's not. We are not there yet, and building a digital twin of the Earth. So, but still, so there are lots of pieces that need to be solved. Yeah.
I guess the discussion about the ethics in connection with AI is very interesting now, and we have to be aware of where the technology brings us, and be able to put a stop if it's used in an unethical way. Mm. So legislation is very important, I think.
Yeah, well, that's a good end. I think saying we have to think about ethics of what we do as scientists. We always have. So thank you very much, and thank you very much everyone for attending, and I hope you have enjoyed the session and learned something new today and bring it out into the world. Yeah, thanks.